So we have 4 to 2. So we want to get the energy of 4, negative 1.36 times 10 to the negative 19th. I can't see it. Huh. Why not? Yeah, log out of it. It says you're viewing it. If you're not. Must be the internet thing. There we go. Bada bing, bada boom. All right. Sorry about that. So we have negative 1.36 times 10 to the negative 19 joules. Remember, these lines out here mean that this is absolute value. We're going to subtract from that 2, which is negative 5.45 times 10 to the negative 19 joules. So we'll go ahead and put that in here. Negative 1.36 times 10 to the negative 19 minus negative 5.45 times 10 to the negative 19. We get 4.09 times 10 to the negative 19th. All right, let's go from 3 to 2. So again, we need to use the front page. This is the energy for 3. This is the energy for 2. So if we take a look on these calculators, I can just go up here and change the energy from 4 to 3. 2.42 times 10 to the negative 19. That's 3 minus 2. Negative 5.45 times 10 to the negative 19. So that gives us 3.03 times 10 to the negative 19. And the last one here is from 2 to 1. So 2 to 1, we have, if we delete all this, we have 2, which is negative 5.45 times 10 to the negative 19th. We want to subtract from that 1, negative 2.18 times 10 to the negative 18th. And we get 1.64 times 10 to the negative 18th. Boom, boom. Down here it says when the electrons leap from the 4th level to the 2nd level. Did we do that one yesterday? No, we did this one up here, didn't we? So it says down here, hopefully you guys did this one last night though. When the electron leaps from the 4th level to the 2nd level, 4.09 times 10 to the negative 19 joules of photon is released. That means it was out here, far away from the nucleus, and then it emitted a photon in the form of energy, and it dropped from the level 4, 4th level, down to the 2nd level. That's called the quantum leap, when that electron jumps down from a higher energy level to a lower energy level, and it emits a photon. That photon, we should be able to find, well, we found the energy of that photon. With the energy, we should be able to find the wavelength. So from the formulas on front, wavelength equals h times c over the electron of the energy of the photon. So we can plug these in now. The energy of this photon is 4.09 times 10 to the negative 19 joules. Planck's constant is 6.626 times 10 to the negative 34th joule seconds. And the speed of light is 3.0 times 10 to the 8th meters per second. The If you take a look here, joules will cancel out and seconds will cancel out, and we will be left with meters. So all we need to do is take this times this divided by this. 6.626 times 10 to the negative 34th times the speed of light divided by 4.09 times 10 to the negative 19. We get 4.86 times 10 to the negative 7 meters. And then to go from nanometers to or meters to nanometers, every 1 meter equals 10 to the 9th nanometers. So we currently have meters. So every 1 meter will go on bottom, so those will cancel out. And 1 billion or 10 to the 9th nanometers will go on top. So we multiply that by 10 to the 9th. And we get 486, because it's times 10 to the second. So we move that decimal over 2, 486 nanometers. The only reason we do that is because 486 nanometers is an easier number for us than 4.86 times 10 to the negative 7. Yesterday, we showed you that 486 nanometers would be close to, battery died, no, would be close to this color right here. This blue laser pointer. This bottom one here, when the electron leaves from the 3rd energy level to the 2nd energy level, 3.03 times 10 to the 19th joules of photon is released. Basically, they want you to set this up the same way. So that means that this is going to be one of those problems that you're going to have to be able to replicate on the quiz. But the cool thing is, if you practice both of these problems, then you should not have any problem at all replicating the ability to do that. You will be given the formula. You'll just have to rearrange it. You will be given Planck's constant and the speed of light. You will have to find this energy by using this equation. So the cool thing is we can go back up to that where it says 6.626 times 10 to the negative 34th times 3.008, and then we just change that energy there, 3.03 times 10 to the negative 19. Hit enter. We get 656 times 10 to the negative 7. 6.56 times 10 to the negative 7 meters. Now again, if you know your stuff, you know that whenever you multiply these two, you can take negative 7 plus 9. And that will give you 6.56 times 10 to the second. That's a math trick. That's how you deal with exponents in math. Or you can put it in the calculator if you want. Either way, you're going to end up with 656 nanometers, which we said is close to this color, right? Take a look. The wavelength for this is, can we get it? 650 plus or minus. See if I can bring up the thing. Even worse. That's the problem with digital technology, but right here, it says 650 nanometers plus or minus 10. So that means it can be anywhere from 640 to 660. So that's what color you get when you have that. You get that red color. The bottom paragraph down here tells us photons are always released when electrons move from a higher energy level to a lower energy level. Visible photons are only released when electrons move from higher levels back down to the second level, n equaling 2. That's why these two were chosen. 486 and 656 are within our visible spectrum. The other ones up here, like this one, that would be infrared, and this one would be ultraviolet. We cannot see those, right? We cannot see those colors. Remember, a camera can see them. So if I press this button right here, you can try this on your remote as well, but we can't see that in class. You can't see that, right? I'm pressing the button, but when we put the camera on it, we can see it. It's invisible up here. I wonder if you can see it reflecting off, like you can. So you can see it in the camera reflecting off my finger, but in class, they can't see that because it's beyond our spectrum. The camera changes it to a visible representation that we can see. And this is how you make cameras that, you know, can see in what we perceive to be as dark. We could bombard this whole entire room with infrared radiation. Nobody in here would be able to see. The camera itself would be able to see. Can we try it? We're going to try it. I don't know how this is going to work for you guys, but we're going to try it in here. Let's see. I've got an infrared radiation generator. You ever seen footage like of people in a haunted house? Yeah, right. Now the weird thing is that people can use this technology to see through leggings. You know, the leggings that some people wear? They can actually bombard that person with infrared radiation and see through that fabric. Like kind of like X-ray vision, yeah. They do this in like in the airports. They have the technology that bombard you and then basically look through your clothing. Like even a pair of jeans, they might be able to penetrate a pair of jeans with it. This one, not that powerful. So here's my infrared emitter. By law, this one has to be able to be seen, but they actually put something on there so that people could see that this was emitting that. That way, people could not use this technology, misuse this is probably the best way. How can we make this room perfectly dark with all these computers? I'm gonna have to, let's see how we can do this. I'm gonna have to turn that off. All right, the room is pretty dark at this point, as you guys can see. I think I may have to turn this one off too. Let's do that. I'm still sharing my screen, aren't I? Let's see. Maybe not. So this room is, you can see how dark the room is. Now look at this camera right here. Oop. So you guys cannot see his face at all. Take a look. Even if you're in the room right now, oh, my hand's in the way, isn't it? Even if you were in the room right now and you looked back there at him, you would not be able to see him. But this is the room itself. And we can actually look around and see every person in the room. And it's not as good of a transition on film to film as I would like it to be. But again, this is what we're actually able to see. That's the infrared emitter. Now for us in class, it doesn't look like that bright, but that's what we get. Now just to show you guys, let's see if I can move this camera around a little bit better. Can you see yourself? Right? Everybody in the room, can you see her? No, right? Isn't that crazy? Can you see yourself? Right? It's insane, isn't it? Now imagine if they didn't require this to be on there so that you could see that and know that you might be getting recorded or whatnot. Somebody could use this for, spy stuff, basically. The crazy thing is, sorry, those of you at home, but you're not going to be able to see this as well, unfortunately. But I'm going to show them real quick. Take a look at this. We could actually read this if we had footage of it. You can actually see the words on that page. Crazily enough. Can you read that? Yeah. All right, guys, that's it for today. This week was kind of a weird one. Don't forget on Monday, asynchronous. Let's check. I think I've already figured out what I want to do. Let me check real quick before you guys skedaddle out of here crazily. Yeah, can your guys' cameras on your phone pick up if I do that? You guys can try that out. I'll bombard the room with some radiation. You guys can see if you can actually pick it up with your cameras on your phone, maybe. What's that? Huh. February, what is today? Wow, I messed up on making the dates on this thing, didn't I? 19th, look at that. I did not change the dates on here. Where were you on me on there, Anna? 16th, 17th. Anne, sorry. 18th. Where were you on that? 19th. You don't know? What is your whole name? Annabelle? No? Oh, okay. So I don't know what we are doing next week for asynchronous. I thought that I did. It's weird. But we'll get that figured out. So you guys can get out of here. We've got about, I think, about 14 more minutes, but you guys can get caught up if you need to. If you haven't done that test and you need me to reopen it for submission, make sure you get on that quiz over electrons. Make sure you get on that. Cool. See ya. Anna Jade Gables. My mom's name is Lita Ann. Just kind of a peculiar name, but.
My grandfather read Anne Gables. My mom, she was a kid, as a bedtime story, and so
That's how it got stuck.
Yeah. And then my brother was named after a movie character.
What's his name?
Graham.
What movie?
Homework's The Holiday.
Haven't seen Homework's The Holiday.
Hallmark.
Yep. Hallmark movie. Were you able to get? Was your camera able to see in the dark?
Oh, I didn't do it. It can see very good.
I could have swore I had the movie we were going to watch on Monday. Hmm. We're done with all the mysteries of matter, right? I gotta grade those soon. Hopefully over this weekend. Hmm. Mhm. Yeah, right. Isn't that crazy? It's insane. Yeah, her whole laboratory is basically locked up. You can't get in there unless you have a suit on. Crazily enough. Hmm? Oh no. Keep the spray down. How's that this weekend? Everything fun? What is it? Then you go to the gym, get 12. Have a good one. Sorry. Didn't mean not to try to trick you or anything. Have a good day. are you guys?
Good, how are you?
Wow.
More periodic tables. I lost mine.
How many have I given you? Like 100?
One.
Just one?
Yeah.
Seems like so many.